Today we're going to look at selecting an appropriate function model to model data. And we'll look at different contexts, data graphs, and appropriate situations to use one function over another. So on this first table here, we're going to look at tables. When we're looking at tables, you want to look at what is occurring on this table. So we see there's equal length intervals on the top here by 1. On the bottom here, we see that the difference is 5, 5, 5 each time. So we have a constant change there. So we know that this should be linear. On our second example here, these are still equal length intervals up at the top where it's 1, 2, 3. But on the bottom here, it went up by 2 and then went up by 4, 6, 8, and 10. So this is not linear because it does not have that constant rate there. So we want to look at something else. When we look at this, we see that the difference here is 2, 2, 2. So our second differences are the same. So we know this is quadratic. You've also heard it said as it has a linear rate of change. And so that makes it quadratic. When we look at this third table here, and I check my differences, that's always a good way to start is look at your differences on the table when you have equal lengths, especially, or check the rates of change. Those are the two things you want to look at first when you see those tables. Those were not the same differences, so then I check my second differences, and so that's 12, 18, 24, and 30. And so this is not quadratic because the second differences are not the same. But when I look at these numbers, I recognize that they are going up by 6 each time. So the third differences are the same. So this is cubic when the third differences are the same. All right, this last one doesn't have an equal length up on top. This is a difference of 2 right here. This is a difference of 1. Then it goes back to 1. Then it goes to 2 again, and then it goes to 1. In this case, you would want to check the rate of change instead of just the differences. And this is 6. This is 3. 6. And then 3. And so if I check my rates of change here, I would divide the difference in my y's over the difference in my x's. And so I get 6 over 2, which is 3, and 3 over 1, and 3 over 1, and 6 over 2. So this has a constant rate of change, so it is linear. So you do want to look at those data points and investigate them a little bit more if needed. So first difference is the same, linear. Second difference is the same, quadratic. Third difference is the same, it's cubic, and it does continue from that, so quartic would be fourth differences. You can check your average rates of change. If those are constant, it's linear. If the second ones, then again, it would be quadratic. Another way of looking at it is thinking about the context of the problem. So here's some geometry ones. In some problems, you're going to see something like perimeter, area, or volume, and you need to think about what kind of function would represent that data. So for perimeter, for example, we would have the length, and this would be the width, and we would add up all of those sides. Now, let's say that the length was x and the width was x plus 6. If I found my perimeter, I would do x plus x. There's my two lengths. And then I would do my two widths, so x plus 6, x plus 6. And so x, and x is 4x, and 6 plus 6 is 12. So we get a linear function here. Now, if we think about the area, length times width here, and we'll just call this little distance x. You've seen these in geometry quite a bit. And we would say this is 6 and this is 8. Now, when we find area, we're doing our length times our width. And so if I thought about this length right here, that would be 2x plus 6, and the width would be 2x plus 8, because we have x is this little piece plus the 6 plus x gives me that 2x plus 6, And then on this side, it would be x plus 8 plus x, which is 2x plus 8. Now, when we multiply this out, the 2x times the 2x is going to give me an x squared, 4x squared. And so that would be quadratic because it's got the x squared. If we think about volume, then we're doing the width, the length, and the height. And so our volume would be equal to the length, width, and height. So let's just call this x plus 6 right here. And I'm just doing an example, an x plus 2. Then in this case, we would be multiplying x times x plus 6 times x plus 2. And the x times the x times x is going to give me an x to the third power. And this is cubic. So when you're looking at some of the geometry context, keep that in mind. Perimeter would give you a linear function, area would give you a quadratic function, and volume would give you a cubic function. All right, so we're going to look at some of the restricted domains as well and some of the word problems that come from this. It says a bottle rocket is set up on a picnic table. When the firework detonates, it will shoot straight up and come back down. The height of the bottle rocket is modeled by this equation. And this is plus 2 here, but it should be a squared up here. So if you'll just fix that on your notes, negative 16 t squared plus 64t plus 3, where t stands for the time in seconds and h in height of the rocket in feet. So I'm just going to sketch a picture just so you can think about that. It said it was on a table, so it's going to start from right here. And it says it goes up and then back down. So when we think about that scenario, that's a quadratic. So you want to think about what that route would look like so you can think about what function it models. But that's a quadratic. We do have an equation that also shows it's a quadratic because of the t squared. And so now we're going to answer some questions, and we're going to use our calculator to do most of these here. So it says find h of 2, and what does that mean in this context? Because we do want to talk about the context of the problem. And so for h of 2, we would plug in the 2 into the equation, so we get negative 16t squared, which is 2 squared, plus 64 times 2 plus 3. We simplify that in the calculator, and we find it is 67. So in the context of that problem, that means that in 2 seconds, the rocket is at 67 feet. Because x is measuring my time, or t is measuring my time, and so that's the x value, so that's the 2 we plugged in. And then what's coming out of that is the height, and so in 2 seconds, the rocket is at 67 feet. If we think about what is the restricted domain from there, well, anything before this point would be negative time, and so that doesn't make any sense. 0 time would be the first point here, and then when it lands on the floor would be our final point there. Anytime after that's the rocket's no longer moving. So to find our restricted domain, we need to find how long it is in the air. So we're going to go to our calculator, and we're going to put that in for our y1. And then for y2, I'm going to go ahead and put in 0 because that's when it's back on the floor. Our height right here is 0. So when I get that into my calculator, into the y equals, put that right there. There it is. I want to look at my graph. And so most of the time our graph looks like this, negative 10 to 10. But we've talked about changing that window. You want to be able to see it better. So I'm going to change the window here to negative 5. 10 seconds is fine for right now. And then we need to think about how high this is going to go. Well, we know it was at 67 right here. So I'm going to go somewhere above that. Let's say 80, not 800, 80. And I hit graph, and that gives me a way better picture of my bottle rocket. Now I hit second trace intersect because I put that 0 in for y2. And so I want to get close to that point I'm looking for right there. And I hit enter, and then enter for the second curve at 0 and enter for the guess. And so there's my intersection at 4.046. And we want to keep 3 decimals when we're doing this. So our restricted domain would be from 0 seconds to 4.046 because that is when it's back on the ground. Now, what is the restricted range? Range is our y value. So we know the ground, that would be the restriction. It's not going to go underground, so we don't need any of the negative numbers. And then we would need this top point right here, and that's called our vertex. That's the max height, and we did that in polynomials. So if you remember, we hit second trace, and we want a maximum there. That's the highest point, and so I'm going to go somewhere on the left-hand side, hit enter, somewhere on the right-hand side, hit enter, and then enter for the guess. And so that's 1.9999967. Well, I remember that. That's the point we plugged right in there. So coincidentally, this is our vertex right here at 267. And so our restricted range would be from 0 to 67. All right, and since we always want to be practicing that average rate of change, it says, what is the average rate of change for the interval from 2 to 3 seconds? So I've got 2 seconds right here is at 67. We would need the 3 seconds. And so again, I can use my calculator to do that. I can hit second table and just go to 3. There it is at 51. All right, when we calculate the average rate of change, remember that is the difference in your y's over the difference in your x's. So I need F, sorry, I said F, that's H. H of 3 minus H of 2 over 3 minus 2. And so H of 3 we said was 51 minus 67 over 1. And so that's negative 16 feet per second. So that would be our average rate of change from these 2 points right here. It's negative. We can see that our graph is decreasing right there, so that's why it's negative. And it's going at that rate of 16 seconds. All right. On the back here, we have a piecewise function. That one's one of the contextual ways that we want to look at this as well. So it's not just one function, but it's going to work in little pieces. It says the graph of F below shows the price of Frisco High School yearbook. The yearbook sells for $40 for the first 5 months of school. After that, the price increases every month. So then our first 5 months right here, it is selling at $40. Then the next month it goes up to 50, the next month up it goes to 60. Now the entire month it is at $50 here. That's why we have all of this until that first day of the next month when it goes off to the next price increment. All right, so what is the domain in the context? It would be from 0 to 9 months, which is the school year here. Okay, then what is the range of the context? We just said $40, $50, $60, $70, and $80. There's no values in between these, so I don't want to write that as an interval because I don't want to include these right here. That's not it. The price will never be 45 since it jumps from 40 to 50 and so on. All right, to find F of 5.5, what does it mean in this context? So I would go to 5.5 right here, and the price is $50 because that's after the 5th month. It's already jumped up to the next one. Now it's before the 6th month. So the whole month right here, it's $50. So this would be $50. At 5.5 months, the yearbook will be $50. All right, the last model that we're going to look at is the inversely proportional. You probably did this a little bit in Algebra 2, so hopefully you remember this. Anytime that you see these words inversely proportional, we set up our equation similar to this right here. It's a proportion, so we're going to have some constant over our value. It says the force of newtons exerted by a magnet on a metal object is inversely proportional to the square of the distance in centimeters. So when I set this up here, the force is equal to some constant over the distance squared. So by giving us that information right there, that inversely proportional, then they've told us the setup looks like this. Now they're always going to give you some information so that you can find that constant. If a magnet exerts 60 newtons on a metal object 2 centimeters away, what will be the distance when the force is 10 newtons? So the first thing, again, we need to find that constant. So I'm going to plug in 60 and 2 for my centimeters. And so 2 squared is 4, and we cross multiply when we do proportion. So this would be 240 is equal to K. So the equation is the force is equal to 240 over the distance squared. So this would be the model for this data. Now to find our final one here, where it says, what will the distance be at 10 newtons? Then I plug in 10 for the force, and I'm solving for this d squared. We cross multiply, so we get 1040 is equal to d squared. Sorry, 10d squared. Lost my 10. I divide by 10, and so we get 24 is equal to d squared. In order to get rid of the square, I'm going to take the square root. Now, anytime you take the square root of a square, you need the positive and the negative. But because we're talking about distance here, that would be outside of that domain. So my domain would be 2 root 6. Or if you put that in the calculator, 4.899 centimeters. All right, the last thing I want to talk to you about is from a graph. And so we don't have the types right here, but I do want you to know you should be able to recognize if I put my data points looking like this, then I know that looks linear. So I would pick a linear model for that. If I graphed my data points and it looks something like this, then I know that's quadratic because it looks like the U shape, the parabola. If I put my data points and it looked like this, then I know it's going to be a cubic function. So you do have to use all of the things you know about the previous functions to help you as well. Something like this. Well, I know that if it looks like this, it has to be quartic. If my data look like this, it's getting really close to the x-axis and then it's going up, or it's coming up from the top and getting close to the x-axis, then I know that's exponential. Its inverse that you saw in Algebra 2 is the one that gets really close to the y-axis and goes that way. That's logarithmic. In pre-cal, we're going to study 2 other ones. If our graph looks something like this, that's logistic. And then another one we're going to study cycles up and down like this, and that is sinusoidal. So the sine curve. The calculator helps us get some of these as well, so we can do regressions for all of these in the calculator, which is what we're going to do in our next lesson. But I want you to understand that you can graph the data and see what kind of model you would want to use. Again, if it says inversely proportional, you're going to use rational. You can think about the geometry that's going there. Perimeter would be linear, area would be quadratic, volume would be cubic. You can look at the differences on your data to see what that does. You really want to dig into the information in order to determine and use what you've learned about those functions. All right.